All right, so chapter 4 is titled Reactions in Aqueous Solutions. So, AKA, we're talking about things with water. I would say about 25% of this is going to be review, and the rest of it is going to be new materials. So, let's go ahead and get started. So, take a second and look at these 4 different substances. I realize that these are 2 ammoniums and 2 sodium chlorides. Can anybody pick which one doesn't really fit? And it's not for any other reason like that they're different compounds. That's not going to be the reason. Does anybody know who doesn't fit and maybe why?
Is it Is it like NaCl because it's like solid?
Okay, so that's a good guess, and that's usually what most kids, I think, want to guess, and it's not. So the guy that doesn't fit is ammonia, this ammonia specifically. So ammonia gas is a pure substance. Sodium chloride solid is a pure substance. Sodium chloride gas, and you go, how in the world do you turn table salt into gas? Well, if you heat it up really hot, you can technically turn it into a gas, but either way, it's still a pure substance. An aqueous substance is a mixture, meaning this is ammonia also in the presence of water. So there's actually 2 things involved in here, and that's why the ammonia aqueous does not belong. Okay, so let's move on. So this is a big, huge, enormous water molecule, okay? This is the oxygen end. The red is the oxygen, the white are the hydrogens. And water has something special about it that you've probably learned. Water is polar, okay? It is polar, which means it has what's called a dipole, okay? And because it is polar, the oxygen region of the water molecule is slightly negative. That's what this little symbol means. And the hydrogen atom region of the water molecule is slightly positive, okay? That's what makes it polar. So water is the solvent in any sort of aqueous solution. Okay, so if you take a look at this, this is a sodium chloride formula unit. It's in a crystalline structure, like you know all salts to be, being ripped apart by water molecules. So the water molecules are weaseling their way in here and pulling apart the ions of the sodium chloride to break it apart. This is literally showing you the dissolution or the dissolving of salt in water at the molecular level. Now, what's really important about this slide is that the water molecules are orienting themselves a specific way around the ions when it weasels its way in there. So let's look, I'm going to draw my next slide. Let's look at the chloride ions. So this is a salt ion, okay, a bunch of ions, it's called a crystal lattice, okay? And I'm going to draw my chloride ion, okay? It's right here. This is just one chloride ion. So I'm going to draw the chloride ion, and then I'm going to notice that when you find the chloride ion, so there's one here, and there's one here, and there's one here, the water molecule is oriented so that the hydrogens, which I'm going to draw them tan, okay, because like I can't draw white on white. So these are hydrogens of the water molecule are facing, this is my oxygen, this is my oxygen, this is my oxygen, okay? The hydrogens are the ones facing the chloride ion. Why? Anybody know why this is?
Polar, not polar? I don't know.
It is a polar thing. It does have to do with that, yes.
Chloride's negative, and the hydrogen wants to bond with that, so that's why it's closer, because hydrogen's positive.
Beautiful. So the hydrogen region of the water molecule is slightly positive, right? So it is attracted to the negative part of the salt, which is the chloride ion, right? It's Cl minus, okay? Now, I want to be clear. They are not attached to the chloride ion. They are just attracted to the chloride ion. So they orient themselves around the chloride ion in a specific manner. They call these hydration, because water, shells because they're surrounding the ions. Now, let's look at the sodium ion. So the sodium ion is represented by the purple sphere, okay? If you find all of the sodium ions in here, you will see that the water molecules are flipped now. The oxygen, which is the red, are pointed at the sodium ion. So the oxygen part of the water molecules are pointed towards the sodium ion, and the hydrogens are on the outside. So why is this?
Because the oxygen is negative.
The oxygen is partially negative, and the sodium is
positive, partially positive.
positive, okay? So the oxygen, or the sodium is fully positive, and the oxygen is partially negative. So there is an attraction, they don't attach, but there's an attraction between the partially negatively charged oxygen to the positively charged sodium. So they form these little hydration shells around them, and it's represented like that in this diagram. Literally, this is showing you how the water goes in and dissolves or breaks apart the salt. You're watching the dissolution of salt or the dissolving of salt at the particulate level. Do you have any questions about that? Okay, let's keep going then. So, I want you to take a second and I want you to try to figure out who you think this is. So this is an aqueous solution with ions floating around in it. Anybody know who you think it is and why? Justifying your answers is a big part of this class. So I want you to pick A, B, or C, but I also would love to see a good explanation of why it's A, B, or C. Anybody? So C, it is C. Andy said C. So the reason it's C is because potassium is +1 and sulfate is -2. So I see these -2 for the sulfates and these +1s for the potassium. There's something more. What do you notice? There are 1, 2, 3, 4, 5, 6, 7, 8 potassiums. Okay, and there's 1, 2, 3, 4 sulfates. Look at it. There are 2 potassium ions for every sulfate ion. So that makes sense that there's double the potassium ions in here. They didn't just show the ions, they also showed the correct proportion of the ions relative to each other based on the formula. Do I have any questions about that? Okay. So let's keep going. So what is a salt? A salt in this class at this point is any sort of ionic compound, okay? And any metal, nonmetal, or metal polyatomic can be termed the word salt. So I want you to circle every single thing that you think is a salt right now. Everything that you think could be considered a salt. Metal, nonmetal, metal, or metal polyatomic, or anything that is +1, -1, +2, -2, anything that has opposite charges. So metal, non-metal. Hopefully we circled this guy. Metal, non-metal. This is an acid. Acids are not salts, they are acids. This is also an acid. Non-metal, non-metal. That is not a salt. That is a molecular compound. Okay, I'm going to skip this guy for a second. Non-metal, non-metal, molecular compound. Metal, polyatomic, boom, salt. +1, -1. These are perfect ion cation. Salt. I know that this is not all nonmetals, but this is a +1 and a -1. This is an ionic compound. Okay. Now, be careful with this guy. This is not hydroxide. This is an alcohol group. This is methanol. Okay. So it does not break apart. It's not +1 like -1. This is a molecular compound. It's an organic compound. So I'm not going to circle it. Do I have any questions before we keep going? All right, so notice that in this is showing a methanol molecule, which is a molecular substance. It's not ionic. Notice that in the presence of water, it looks so much different than it did with the salt, the ionic compound, right? The ionic compound was the water went and weaseled its way in and kind of ripped it apart. Now, methanol water doesn't have the ability to do that with methanol because methanol doesn't pull apart into ions because it's a molecular compound. So water readily mixes with methanol because they're both polar, which isn't something you necessarily need to know right now. Because they're both polar, but it doesn't go in and like pull the methanol apart like it does with ionic compounds. It's a totally different type of mixing. Okay, so again, or to move on from that, anything that it breaks apart into ions, charged particles, is called an electrolyte. And electrolytes conduct electricity. Okay, they conduct electricity. And they are able to do that because the electricity is a flow of electrons, which are charged particles, and electrolytes have charged particles floating around in them. So anything that can break up into positive and negative charge is considered an electrolyte and has the ability to conduct electricity. So you might have heard the word electrolyte in like everyday life. Where have you heard the most what's one of the most common things you hear about electrolytes with?
In sports drinks.
Okay, sports drinks like, I don't know, Gatorade. Okay, we'll just use that as an example. So Gatorade has a bunch of sodium and potassium ions in there that are electrolytes that float around in there. And now if I tell you that it can conduct electricity, what does that mean? Well, I usually do this as a demo, so I think I'm going to have a demo day next week for you guys so I can kind of show you some of these demos I've skipped over. I have this light bulb. And it's not connected. I plug it in, but the circuit is not complete. It has like these two prongs that come out of it, and they're not connected. So even though electricity is flowing through it, the light bulb won't go on until the circuit is complete. Okay, so I can complete the circuit with different solutions. If I put Gatorade under here, and there are electrons flowing through it, and the Gatorade goes under here and completes the circuit, literally the light bulb goes on because Gatorade has ions floating around in it. It contains electrolytes, therefore it can conduct electricity and literally power the light bulb. So I know that sounds weird to you and kind of crazy, but I'm going to prove it to you. Okay. Things that don't break apart into positive and negative charges are not electrolytes, or also known as non-electrolytes. So this is like all of your non-metals, like non-metals with other non-metals, with the exception of your acids. Most acids are non-metallic. However, acids are a whole nother category. Okay? Strong acids like HCl are strong electrolytes, aka even though this is a nonmetal with a nonmetal, strong acids completely dissociate or ionize into their respective ions. Now, if there's ions in there, it is called an electrolyte. It is the ability to conduct electricity. Okay? For the sake of this class, weak electrolytes will be weak acids and weak bases. So, for example, hydrofluoric acid. I'm kind of running out of a little room. HF is a weak acid. What does that mean? So this is like my example of a two-way arrow that you might not be familiar with yet. H plus plus F minus, okay? What this means is that this acid like kind of dissociates into ions. Maybe 1% of the acid turns into ions, and the other 99% of it stays intact, meaning it doesn't break apart into ions. It stays as just HF attached to itself. But because there are still tiny bits of ions, of charged particles, it does conduct electricity. It just doesn't conduct it very well. So that's why we call it a weak electrolyte. Like, it will conduct electricity, just not as good as something like hydrochloric acid, which totally breaks apart into ions. Questions so far? Okay. Why is this in my way? Okay, so this is going to be the harder part. We are going to need to memorize our strong acids and our strong bases. Once you have these memorized, anything that isn't a strong acid is by default a weak acid. And anything that isn't a strong base is by default a weak base. So here are your 6 strong acids: HCl, HBr, HI, perchloric acid, nitric acid, sulfuric acid. Okay? This is the 6 of them. If you are not one of these, you are not strong. You are by default weak. All other acids are weak. Now, here's what's interesting, and this is why most kids get this mixed up. You see hydrogen with a lot of the halogens, hydrogen and chlorine, hydrogen and bromine, hydrogen iodine. HF, which F is also a halogen, is not a strong acid. It is a weak acid. So do not let that mix you up. Kids always want to put HF here because they see the Cl and the Br and the I, and it is not strong. It is weak. Okay? All right. For your bases, pretty much for the sake of this class right now, anything that has hydroxide in it is a base. Now, if you go to your periodic table, basically any alkali metal right here with hydroxide is a base. So all of your alkali metals are +1 and hydroxide is -1. So LiOH, NaOH, KOH, RbOH, CSOH. If you look at the list, you'll notice I did not include francium, and the reason that is because francium is radioactive. So you aren't really going to see it have the ability to form a base. Okay, so I just didn't include it. But pretty much all of your alkali metals, remember hydrogen's not an alkali metal. It's just sitting here because it has 1 valence electron like all the rest of your alkali metals. So all of your alkali metals with hydroxide are strong bases, plus you've got 3 from your alkaline earth metal family, CBS, calcium, barium, strontium, CBS. Okay, notice that when you write the bases for your second family, that there's 2 hydroxides. And the reason that is because calcium is +2 and strontium is +2 and barium is +2, while hydroxide is -1. So they consider these heavier because you actually have double the hydroxides in them. Okay, do I have any questions so far? Okay, if you react a strong acid, that's what this means, and a strong base, that's what this means, your net ionic equation will always be H plus OH minus makes water, unless for some reason the acid-base reaction produces a precipitate, also known as a solid, okay? So acid and base neutralization reactions are ways that we get salt, because acids and bases make salt and water. Okay, this isn't the only way to produce a salt, but it is a way we can get a salt out of a reaction. So I'm going to prove this to you. We're going to practice net ionics, which you should have learned last year. So here we go. HCl is a pretty common strong acid, and it's aqueous. Okay, plus sodium hydroxide is a pretty strong base. It's pretty common for a base, and I'm going to assume it's aqueous. Now, it is your job to predict the products. So this does look like a classic double replacement reaction, and in fact it does replace that way perfectly. However, it's technically called a neutralization reaction because it's an acid and a base neutralizing each other. Now, it will double replace the way you think. The H will go with the OH, and the Na will go with the Cl. So I make NA's plus 1, Cl's minus 1, and I make HOH. Well, HOH is H2O. So like this is water. So I'm going to erase that real quick because I'm going to write it as H2O. But HOH is water. And then you need to balance. 2 hydrogens, 1 chlorine, 1 sodium, 1 oxygen, 1 oxygen. So everything is 1 to 1 to 1 to 1. Now, you need your solubility rules. So, solubility rules. So let's look at those guys. Back in the day, maybe like 4 years ago, everybody in AP chemistry had to memorize this entire chart. So like you had to know all of the exceptions and everything. You do not need to do that anymore. You do, however, need to memorize these first two. Pretty much you need to memorize the substances that don't have exceptions, meaning they're always soluble, which means they're aqueous if they're produced in a reaction, okay? I'm telling you, here's the most important on these. Alkali metals and ammonium and nitrates are always soluble. 0 exceptions. Now, here's where you need to be careful. This tool right here, this sheet, is used for predicting products that are ionic only. This does not help you with gases. This does not help you with liquids. This only helps you with ionic compounds that are products. How do you know the state of matter of the reactants then? Well, the problem will have to tell you. You do not use solubility rules for reactants. They are solely for products. So having said that, water is not ionic. You should know the state of matter of water in a normal given situation, like at a normal room temperature. What state of matter is water at a normal room temperature? Liquid. Great. Look it, you're not going to find water on that chart. This chart is not for molecular compounds. This is for ionic compounds only. So like we did not, but let's say we produced O2. Let's say we did. You're not going to find O2 on that solubility chart. O2 is a what?
Gas.
Gas, okay? So there are some of them that just have to be common sense. That chart is for salts only. Well, this is a salt. So if you go look at that chart, you will find out that alkali metals are always soluble. There are 0 exceptions. I don't even care who its partner is. So boom, soluble means aqueous. Now, do you remember the rules for writing out net ionic equations? So in order to break a substance into ions, it has to be 2 things. Right now and from until now, you knew that it had to be aqueous. You do not get to touch solids, liquids, or gases. You do not get to touch them. You have to leave them alone. You rewrite them as is, okay? Anything that is aqueous plus, this is what's new, a strong electrolyte, so strong acid, strong base, salt, you can break apart. You do not get to break apart any weak electrolytes. You would leave it intact just like you would solid, liquid, gas, okay? Now, HCl is a strong acid, so I'm gonna, I don't want to erase this whole thing. Oh, sorry. Okay, I'm gonna do my net ionic. I'm gonna just show it to you. Here we go. So this is aqueous strong acid. I get to break it apart. So H plus Cl minus plus strong base, aqueous. I get to break it apart. Na plus OH minus makes. This is a salt and it's aqueous. I get to break it apart. Na plus Cl minus. This is a liquid. I do not get to touch it. It stays intact. You do not get to touch solid, liquid, or gases. Okay? This is called my gross ionic equation. It's everything that you can broken into ions and everything else. So from here, I cancel out what are called my spectator ions. Those are the things that you have the same of on both sides. So I have sodium on the left, sodium on the right. Chloride on the left, chloride on the right. What this means is that during this reaction, these guys are just kind of floating around, minding their own business. They're not even part of the reaction. They're just sitting there spectating, doing nothing. The true reaction that's happening is hydrogen ions, acid. Oops, this is a minus right here. And OH minus ions. So what I have left is my net ionic equation. H plus OH minus yields H2O. Please write this down. All ions are always in the aqueous state of matter because you've taken them from an aqueous compound. To be an ion means you are floating around in an aqueous solution. So I just proved to you that if you have a strong acid and a strong base, this will always be your net ionic. So it's the acid and the base neutralizing to make water. Acid, base, water for the net ionic. You learned this last year. You should have, but it may be fuzzy, so that's why we're practicing right now. Okay. So we're going to take a minute and write out how every single thing dissociates, how every one of these substances dissociates. I'll do the first one for you, and then I'm going to let you do the next ones. So complete dissociation is a one-way arrow. Sorry, the formatting is awful for that arrow. It'll let me do a double arrow for some reason, but not that arrow, okay? So to do complete dissociation, which means to break apart, you have to be a strong electrolyte. The weak electrolytes are the ones that go to equilibrium, which I don't need you to necessarily understand that part yet, but they have a two-way arrow because they're like mostly the substance, but a little bit of ions. So HBr, strong acid. Strong acids are strong electrolytes. So I would write HBr, one-way arrow, and it breaks apart or dissociates into H plus and Br minus. I would like you to try the last three on your own, so I'm going to give you a second. All right, so HF is a weak acid. That means it only dissociates or ionizes a little tiny bit. So two-way arrow, H plus and F minus. So there's only a little bit of these guys, but a little bit is still enough to be able to conduct electricity, okay? Acetic acid is also a weak acid. If it's not strong, by default, it's weak. So I'm going to write it like this. I know there are other ways to write it. Weak acids weakly ionize. So CH3COO, this is acetate, and hydrogen ion. Okay? Sodium hydroxide is a strong base. Strong bases 100%. It's assumed that they 100% ionize. So Na plus OH minus with a one-way arrow. Conducts electricity very well. Okay? All right, so we've practiced that. Now, I would like you to take a minute to try to rank these from the strongest acid to the weakest acid based on the drawings. Now, this isn't like just random stuff they threw at the top. There's a reason that they wrote HX, HY, and HZ. Anybody know why they're writing it like that? What does the H represent?
Hydrogen.
Hydrogen, which is like the H in front of whatever it is probably a telltale sign that the substance is an acid. Is that right? So they're saying this is some acid, like maybe it's HCl, maybe it's HBr, maybe it's HF. I don't know who it is, but it's some sort of acid. That's why the hydrogen is out front, because the telltale sign that something is an acid is that there's a hydrogen in front of the rest of the substance. Okay? So please rank them from weakest to strongest. I'm going to give you a second. All right, does anyone want to tell me who they picked for the first the acid? Which one did you pick and why?
HY.
Okay.
Because it was completely disassociated.
Good. HY looks like it's 100% ionized or dissociated, meaning it's broken apart into the most ions, and the acids that break apart into more ions are stronger. So this is the best electrolyte and strongest acid. Now, this part was a little bit trickier. Who's next?
HX.
Okay, so I'm going to do this real quick. So HZ dissociates into more ions. So it is a stronger acid than HX because it's ionized more. Now, it is still a weak acid. It is not strong. How do I know? Some of them haven't ionized at all. If you look at these guys, they have not ionized at all. Weak acids only ionize partially. So this is a weak acid, but it dissociated into more ions, which makes it a stronger weak acid relative to who's last, which is HX. Do you have any questions about that? Okay. All right, so I would like you to take a minute. I'm going to let you do this. I want you to decide whether these are strong electrolytes, weak electrolytes, or non-electrolytes based on what it means. So strong electrolytes are strong bases, strong acids, and salts. Weak electrolytes are weak acids or weak bases. And then non-electrolytes are covalent or molecular compounds made up of most or entirely non-metals. So I'm going to give you a minute and then I'll go over the answers. Okay, so calcium chloride is a strong electrolyte. Metal, non-metal, it's a salt. Nitric acid is a strong acid, so it's a strong electrolyte. Okay, this is an alcohol. It is a non-electrolyte. It's all non-metallic. Now this is an acid. Its name is formic acid, but it's not one of my strong acids, so by default it's a weak acid, which makes it a weak electrolyte. Questions? Okay. So this is just a summary of electrolytes. Strong electrolytes are these three, weak electrolytes are these two, and non-electrolytes are covalent compounds with the exception of acids. Acids will either fall under strong or weak electrolytes depending on whether they're strong or weak acids. Okay. So in 2001, oh my gosh, this is when I graduated high school. So the FRQ, a free response question in 2001, number 5E, you can do this. Like you can already do part of an FRQ. How crazy is that? It says which solution would be the least effective conductor of electricity, and then they want you to explain. So you can't just say solution 1 and then hope you get the points. If you don't explain, you won't get the points. So you want to make sure you have a good justification. So I'm going to give you a minute to look them over. I want you to pick which solution. I want you to do your best to write out what you consider a good explanation. So I'm going to give you another minute to do this. Okay. Anybody want to share which one they picked? Okay, how about I'll tell you, it's solution 4. Anybody want to share who picked solution 4, why you picked solution 4?
It's an alcohol.
Yep.
And those alcohols are not considered electrolytes, so they can't conduct electricity.
Beautiful. Alcohols are not electrolytes. They don't break apart into ions, therefore they cannot conduct electricity. It would actually be a non-electrolyte. I thought something was interesting yesterday. A kid asked, and this wasn't something I was going to point out, but I am going to point it out now. Why is this one shaded? And in fact, it is shaded for a reason. The reason is, and I'm going to have you know this now, this guy's name is permanganate. And the reason this is shaded is because the permanganate ion in solution is purple. Permanganate, purple. So yes, I want you to know that. That's why they've shaded this. They've shaded this saying like, okay, this is going to be some colored solution. These would be considered colorless solutions. Okay. Now, they didn't ask you this, but I'm going to ask you. Anybody know which one would conduct electricity the best? What would be the most effective conductor of electricity? Now, this is a little bit harder. So obviously it's not this guy, right? It's a horrible conductor of electricity. Anybody know or want to take a stab at what you think solution 1, 2, 3, or 5 would conduct electricity the best?
Solution 2.
So I heard a 2. That is the most common answer, and I think that's because you guys are obsessed with salt and you think salt is, it's ionic, right? But this is ionic. This is metal polyatomic. This is metal polyatomic. This is metal polyatomic. So these are all salt solutions. Salt, 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 salt. So I'm telling you it's not number 2. Anybody know which one it is?
1.
It is 1. Did you guess, or do you have a reason you think it's 1?
Nitrate is part of a strong acid, and acids are good conductors of electricity.
Ooh, that is actually a great reason. It is not the reason, but that is it. I appreciate that thinking. It is because when lead 2 nitrate breaks apart into ions, there are 3 ions involved, a lead and 2 nitrates. And these guys is just Na and Cl, that's 2 ions. This is K and this is MnO4 minus, that's 2 ions. This is K and acetate minus, 2 ions. This guy breaks apart into 3 ions. The more ions that are present in solution, the better of a conductor of electricity is. So that was a hard one. Do you have any questions on that? All right. So solubility rules, get those guys out. Solubility rules. We're going to do some practice. So, back in the day, you used to have to memorize this entire thing, right? And now you don't. So we're going to use this. I think we just went over this, I'm pretty sure. We're going to use this. If you do produce a solid, it's called a precipitate. But I have these compounds that I'm having produced as products, and I want you to circle the one only if it is soluble in solution, meaning aqueous. So let's go through it real quick. I'll do the first one with you, and then I'm going to let you try this on your own. So silver chloride. So you go on here, you go chlorides. Okay, chlorides are soluble, but not when they're with silver. So that would be a solid. So I'm not going to circle that guy. Okay, I'll do one more with you. Magnesium sulfide. Sulfides are not soluble, insoluble, aka solid, unless they're with an alkali metal or ammonium. Now, alkali metals are your group 1. Magnesium is a group 2, so it's not an exception. So this is a solid. It's insoluble, solid. So I'm not going to circle that guy. You're only going to circle the ones that are soluble. So I'm going to give you a minute to please finish working on those. All right, so let's see. Alkali metals. This is potassium, always soluble. Circle. Copper 2 sulfates. Sulfates are soluble, and copper is not an exception, so circle it. Okay. Now, we'll talk about mercury in a second, but this is mercury 2 bromide. Now, bromides are soluble, but not when they're with mercury 1. This is not mercury 1, it's mercury 2, so it's going to stay soluble. Hydroxides are insoluble unless they're with like an alkali metal or an alkaline or CBS, I think. So this is insoluble, so I'm not going to circle it. Sulfates are soluble, but not with lead. So this is insoluble, solid. Hydroxides are insoluble, but barium is an exception on there, so I'm going to circle it. Now, I need to show you something. Mercuries are funky. This guy is called mercury 2. Why? Because that's plus 2. Everybody gets confused on this guy. It's pretty instinctive, I think, to want to call this Mercury 2 because you see twos everywhere. But really, this is Mercury 1. Woo! Oh, don't do that. Make that stop. Okay, Mercury 1. And so then you go, well, what? Like, why is this Mercury 1 if there's twos everywhere? Well, look at it. It's saying that there are two mercury atoms. So a mercury and a mercury hooked up together. And the total charge is +2. Well, that means each of them are +1 to get the total to be +2. That is why they call it Mercury 1. It's two Mercury 1s combining to make a total charge of +2. This is funky, and yes, you need to know it. Are there any questions about that crazy little Mercury guy? Okay, so for these, I'm sorry I don't have the directions on here. I gave verbal directions. I want you to practice on your own, but I want you to circle anybody that you would consider a precipitate. So everything that is not soluble, any of these that would precipitate out of solution, please. And I will give you a minute or two. So this is what I got for all of my precipitates. Does anyone have any questions? Alkali metal, always soluble. Ammonium, always soluble. Hydrogen ion, always soluble. Okay, and then these are kind of like ones that have exceptions. Like copper 2 sulfate, I would not expect you to know without a solubility chart, but like potassium carbonate, you do need to know because you need to memorize that alkali metals are always soluble. Questions? We're almost done. So, net ionic equations. I know we just did a practice one with the hydrochloric acid and the sodium hydroxide. So, there are two rules now for net ionic equations. The one rule you already knew, anything that was aqueous you got to break apart. But technically, that's kind of a lie because if it's not a strong electrolyte, you don't get to break it apart. So, like acetic acid, I'm giving you down here, acetic acid is a weak acid. Yes, it's aqueous. You do not get to break that apart in a net ionic. So this concept is newer to you. You probably have not seen this before. So not only does it have to be aqueous, it also has to be some sort of strong electrolyte. So really what gets tricky are your acids. You have to recognize whether the acid is strong or weak to determine whether you can break it apart. So what I'm going to do is I'm going to do one net ionic with you. And then I'm going to let you go. You guys can leave or you guys can practice to finish the rest of the net ionics. So here is the net ionic practices that I want you to be doing. I'm going to do some on the slide, and then here's the rest of them. And then I have all of the answers for you. So I'm not going to go over them, but if you have questions when I see you on Tuesday, I'm going to see you Monday, but we're going to be testing. When I see you on Tuesday, you can ask, but I'm not going to go over them. You should be checking your answers right here. So we're going to do the first one together, and then I'm going to let you guys free. Again, everything that we have done today, like all this new stuff, is not on your test. It is not on your test. This is chapter 4 material. We are doing chapters 1 through 3. Okay? So here we go. Net ionic equations. Let's see. It looks like I have something in the chat, maybe a question. Oh, yes. Okay, so Wednesday, whatever time I see you next, you can ask questions. Okay. All right, so silver nitrate solution reacting with magnesium chloride. So I'm going to actually go here. So silver nitrate, Ag is +1. Did I not say I could write on this? Oh, no. Oh, wait. Yes, I did. Wrong slide. So silver is +1. Nitrate is -1. They go together beautifully. It says solution. To me, the word solution, and to you, means aqueous. Reacts with magnesium chloride. Magnesium is +2, chlorine is -1, so this is its formula. And it says solution, so I assume aqueous. I would like to give you a minute to predict the products. classic double replacement reaction. So the silver go with the chloride and the magnesium's going to go with the nitrate. But because they have new partners, you need to reevaluate their charges. Silver is +1. Chloride is -1. They go together perfectly. AgCl. Plus, magnesium is +2. Nitrate is -1. So I need 2 nitrates. These should be your products, and then you should balance. So let's see, I need 2 nitrates, so I need 2 here, 2 silvers, so I need 2 here, 2 silver, 2 chloride, 2 chloride. Okay, we good. Questions so far? Okay, so now we need to predict the states of matter of our products. So here's how, this is what I was trying to tell you about the College Board. This is how the AP world will do this. They would say, hey, silver nitrate reacts with magnesium chloride and a precipitate is produced. Now, you should know who the precipitate is by default because you have the rule memorized that nitrates are always soluble. This is a nitrate. I don't even care who it's with. So this guy is aqueous. It's always soluble. By default, that makes this have to be your precipitate. That is how they get away with you only memorizing some of the rules. A product will form for a solubility rule you have to know, and by default, the other guy is a precipitate if they say so, if there is one. Are there questions so far? Okay, now here's the rules. Anything that is aqueous and ionic or strong, I can rip apart. Salt, aqueous, I get to rip this apart. So this is 2 silver ions plus 2 nitrate ions. Remember, it gets distributed. Plus, this is aqueous and it's ionic. Magnesium 2 plus 2 Cl minuses. Okay, makes. This is a solid. I do not get to touch it. I have to leave it as is. AgCl. Plus, this is aqueous and it's ionic. It's a metal polyatomic, so magnesium 2 plus 2 nitrates. This right here is what's called your gross or complete ionic equation. It's kind of like your gross income is like your income before all the government like takes all of it, and then you get your net income and you're just sad and lonely and depressed. Okay, so this is called your gross ionic equation. What we're going to do now is we're going to cross off what are known as our spectator ions. Spectator ions are the things that are the same on opposite sides. So I have 2 nitrates as reactants, but I also have 2 nitrates as products. So bye. And then I see a magnesium 2 plus as a reactant and a magnesium 2 plus as a product. So bye. Now, nothing else cancels out. Oops, I forgot the 2 in front of here, right? This was a 2 AgCl. So now I have 2Ag plus 2Cl minus, that's this guy and this guy left over, plus 2, or makes, AgCl. So I've made 2 silver chlorides. Now this can technically be reduced. Everything could technically be divided by 2. So it really, I'm going to write it like this in the reduced form. Ag plus Cl minus forms silver chloride. This is a solid, and all ions are always aqueous state of matter. So what happens is these 2 ions hook up and form a solid. What do the nitrate and the magnesium do? They literally do nothing. They just sit around unreacted, floating around in the solution. This is your net ionic equation. So like your net income is what's left over after the government takes all your money. And so this is what's left over after we've gotten rid of all of our spectator ions. Whew, what a day. I'm done. You guys can work on all of your other net ionics, or you can go to studying for your test. I will be here to answer questions, but this is done for today.